yes, you are audible, ma'am. Can you please turn on your video?
Yeah, sure. Just give me a second. Hello, good evening.
Hello. Yeah, good evening, ma'am, and good
Good
morning for
evening.
you.
Good evening.
Yeah, thank you.
Okay, dear participants, we have with us Dr. Rakhi Mehta. She is a distinguished professional engineer. She resides in Ontario, Canada, with over 25 years of experience in process engineering, academia, and research. She holds a PhD in chemical engineering and currently serves as a lead process engineer at Maratek in Canada, where she drives innovation and process optimization. Dr. Mehta has an extensive academic background, having been a lecturer at the University of Toronto, Canada, and associate professor and head of chemical engineering department at SCAD College, Surat. Her fields of expertise encompass Aspen and Hysis simulation and modeling, separation processes, nanotechnology, nuclear engineering and technology, and process optimization. Renowned for her technical acumen and leadership in chemical engineering domain, Dr. Mehta continues to make significant contributions to advancing engineering practices. We are expecting one more such contribution from your end, ma'am, today.
Sure. Thank you so much. That
Okay.
was a wonderful introduction. Thank you so much, Mr. Taylor.
Thank you, ma'am.
Okay, so is the stage mine? Can I take
Yes,
the
yes,
stage
the
now?
stage is all yours. Yes, yes,
Thank
ma'am.
you so much. Okay, so let me first share my screen because I'm going to share the slides from my side. Let me know if it is visible to everyone.
Yes, ma'am, it is visible. It is visible.
Okay, so let me do it initially like this so that I can share my screen. Okay, so good evening, everyone. So as Mr. Taylor said very rightly that I have been an academician for last 25 years. I was in academia, serving as a associate professor even in Surat for more than like 12, 15 years. And then I moved to Canada. So now I have switched from academia to industry, and yeah, applying all the theoretical studies that I did in past now in a real world in industries. So today's topic that I'm going to take up, it's a privilege and honor, thanks to Dr. Rotliwala for giving me this opportunity. And we will be taking up a detailed study or basically on process simulation using Aspen Hysis for solvent recovery from wastewater. I'm sure a majority of you might be having an idea about Aspen Hysis, which is a simulation tool that is specifically used for optimizing the process. So, coming forward, and you can say coming from a background of Asia, India, right? We know that the norms which are very stricter, even over there, and even in the countries like North America, where you have to be very stringent on the emissions and rules and regulations. The entire FTP is all about the tools which is used for audits and stuff. But I'm going to touch up the point on why simulation is important and how can the people, industrial people, can save on this. Right now, we know that today, this is the intersection. The current condition is the intersection of sustainability, industrialization at the same time. We need to manage how the probability of, you can say, emissions can be prevented. The solvents are used in tons, right, in different applications, whether it is wastewater, which is coming out, contains a number of tons of solvents, right? Either it goes to the wastewater treatment or maybe they are just disposed of, not majority of the time. So these solvents can be recovered, right? So basically what I'm talking here is there is you can say some source of value in that waste also. So how to recover that? The recovery of solvents is a very crucial parameter which we are going to discuss today. and exploring the process modeling and simulation, which gives us a hands-on or tool in order to do modify any kind of process parameters in order to see how it is going to react or how it is going to work in an actual or a real world, right? Because obviously if you're in an industry or if you're working with a distillation column, let's say, or a reactor, you cannot modify, you cannot do trial and errors in an actual industrial setup, right? So this flexibility and you can say freedom we get in simulation. So again, I'm not the brand ambassador of Aspen, so don't take me that way. But why I'm telling you, because we have been using your Aspen as a main tool for optimizing majority of our processes. And I wanted to give you a tool that how we can also do that. Many of you might have come across, because when we learn optimization and simulation, we learn about Aspen. There are many other softwares like ComSol, you have CamCAD, you have Aspen, and you have Hysis. Hysis is more dynamic side, whereas coming down to Aspen Plus is a little bit more on academic side, where the research you have this particular thing is definitely going to work. So let me start with the slides. I do not have more slides. I just have 10 slides. So don't worry, I'm not going to bore you at all. We are going to take hands-on experimental case study. And I'm going to walk you through entire simulation, how to do the simulation, how to optimize the simulation. And in the case, if you have higher loads or more quantities to be treated, or if you have a lower loads and lower quantity to be treated, along with maintaining the purity, how it can be changed, right? There are different process parameters. You have reflux ratios, you have reboiler ratios, you need to have the determined purity that you want to hit. So there are a couple of parameters based on that. You can go ahead and we can do that further. I think there is a hands up. Do you want me to take it right now, Mr. Taylor?
Yes, ma'am.
I think so. There is a hands up. Do you want me to take it
Uh,
right now?
no, no, no. We will entertain all the questions at the end of the session.
Okay. Sorry for
Thank you.
that. So yeah. Okay. So let me continue. We'll be sharing the screen. I hope you can see the presentation going forward. So this is just my small bio, which Mr. Taylor already said. This will be the content of my presentation. I'm going to just introduce you to why we have to do the simulation and why wastewater treatment needs to be recovering solvents before it goes to the water bodies. I'm going to a little bit give you the glimpse of what are the environmental norms that those are followed in North America, basically America and in Canada, and why solvent recovery and waste analysis are required. ROI calculation, which is return of investment, right? In case if you are making an investment of, let's say, particular millions, are you getting it back in how many years it is going to give you the return? And if you're using fresh solvent, how it is you are benefiting or how you are saving on that. So all those things we're going to take. Then I'm going to have a little bit understanding. Going to give you an idea of in the field of solvent recovery, how simulation works, what are the different separation processes that can be taken into consideration or that can be used up in this particular process. So that those that we are going to take up. Then we are going to go over process requirements for modeling, right? And basically, if I'll be taking that by showing you a case study. It's a simple case study, but I've taken not complicated one just to give you an idea. And I'm going to modify it accordingly. And I'll show you the changes based on that. And then at the end of the session, I'll be taking the questions. So, process modeling and simulation, if we talk about, right? So it's you can say, it is basically the concept where you are ensuring the economic feasibility, right? Because the solvents which you are buying every time you are buying virgin solvents for any of the process, right? It has too much of cost. At the same time, we have to have environmental compliance, right? Because there are emission rules, there are the rules and regulations which needs to be abide by the different provincial governments, at the same time the federal ones, right? So any professional, whether you are a researcher or you are working in an industry or you are an academician, I believe understanding the Aspen Hysis for solvent recovery would be definitely cost saving. At the same time, you can say it's the thing of today, right? So coming down to what is Aspen, it's nothing but a virtual model, okay, of chemical processing. I'm not sure, like I'm sure like many of you might be knowing about the background of how this Aspen work and what is the process simulation, because we learn it during one of the subjects in chemical engineering, and I assume that majority of you are from the background of chemical engineering or environmental side. So that's the reason I'm not going much in detail of how does it work, but I will be focusing on how to use it basically. So the softwares that generally where these modeling use are called the thermodynamic. They are based on thermodynamic principles and mathematical models. So which is fitted in. And the best part of these kinds of simulations is they are having database of all this, you can say, chemical components or chemical compounds which we want, whether it is boiling point, latent heat of vaporization, whatever is required in order to determine certain properties, right? We used to do Anton equation, calculate vapor pressures on our own using maybe Excel or maybe the calculations on the one side. But using simulation, this becomes very easy because half of the job is done, right? So basically, application wise, it is very much important, and focus on these slides because your questions are from these ones only. So you have optimization of process parameters, sizing of equipments, feasibility studies on the one side, the what if scenarios, that in case if I change this parameter, how is it is going to affect my product, or how it is going to give me the product at the end of the process. Is it going to increase my waste disposal cost? Because that is also one of the issue which many of the industry people maybe come across. Then you have evaluating new technologies. Let's say you are introducing or getting into a new technology and you want to check whether it is working or not. The process parameters, the temperature, pressure, vacuum, whether it is working or not. So all these things are very much helpful. Another most important thing is sizing of equipments. Let's say you are designing a distillation column. So up till now, we were using the MEHTA method. Obviously, now it has been, you can say, optimized, and the simulation has taken a very big leap into this, where we can design a distillation column, we can size it, diameter, height, packings, whatever you want to change, right? And it gives you the perfect parameters at the end of the process. Definitely, you have to consider the efficiency factor of the plates and the trays or packings, whatever you are talking about, right? So yeah, that's what the simulation is all about. Coming down to the environmental norms, as we have stricter norms even in India, I know about GPCB norms because we used to work in audits and stuff. So at that time, we used to have some touch on the norms that are followed by government in order to maintain the emissions, whether it is water, air pollution, or it is soil pollution. So even North America, maybe whether it is U.S. Environmental Protection Agency, which is the biggest one in USA, it's federal one, right? The federal government works, or maybe it works along with the provincial ones. Provincial means states, right? So they work hand in hand in order to maintain the purity level of air, water, and land, whether it is clean at their act, national pollutant discharge elimination systems, or toxic substance control, which is basically for the hazardous system. They also work on the climate and energy regulations to see that, again, we have to take care of global warming. And then similar ways, Canada has Environmental and Climate Change Canada. Under that, you come, that is Canadian Environmental Protection Act, Wastewater, and Climate Change and Sustainability. So each and every country has its own set of rules. Let's say if you go to Europe, Europe has a very stricter rules of this. Similar ways, each and every country has its set whether it is, you can say, land pollution or air pollution, there are very stringent laws depending upon the area and depending upon what type of industries are located over there, right? So, and that is the reason we have to think about that why we should, I mean, how can we recover solvents, purify water, and that water goes to the water body so that you do not have too much of waste disposal at the end in order to dispose that off. So coming down to significance of solvent recovery, why you require, I've already discussed a couple of things. You have the purification, the pure solvent which is produced at the end of the solvent recovery, right? It is closer to the purity that you require, and you can adjust the purity according to your requirements. Now, these solvents help you in mitigating the issues of sometimes there are shortages, right, in the production or in the supply of the solvents. So this plays a very important role in order to have that logistics like solved for you. You do not have to worry about the shortage of it. The second important thing is again economic feasibility and operational charges, which is or a costing that it comes down to, right? So it is reducing too much of, you can say, costing towards fresh solvent and disposal cost. It is sustainable, of course, because it generates less footprints and less waste generation in overall. The regulatory compliances, which is one of the most important thing which needs to be understood, and the emission limits that you have to meet to. So those things are also taken care of. And then most important thing is improved efficiency, right? So all these you can say in a package, a strategic approach when you do it, it is definitely going to be going a long way towards the regulation, compliances, and efficiency improvement. Coming down to ROI calculator. So what is an ROI calculator? Let me just give you basics about before I show it to you. So when any of the companies, let's say you are using ethanol, or maybe you're using acetone, MIK, or you're using any other solvent, let's say if it's low boilers or high boilers, right, in your industries. Now, many of this, let's say benzene, they have carcinogenic effects also, and they have their, you can say, waste disposal cost also associated with it. Every time when you purchase fresh solvent, you are going to have that much of cost in, right? So what does this ROI calculator do? It's from my company's website. I've just used for giving you an understanding that when you add the numbers to this, it will tell you how you are saving or how much gallons of pure solvent you are saving on this, right? So I hope you can see that. So this is the return on investment calculator. Uh, how many drums of waste do you produce per month? Let's say, and this is just the numbers given to you in brief. So if you see over here, you have 2 drums per month. You're producing 2 drums per month of this particular waste solution. What does it cost to dispose 1 drum is, let's say, $100. How much does it cost to purchase a new drum of solvent is around $440. And what is the percentage of contaminants that are present in each drum? So let's say there is 80% of water, 20% of contaminants. This contaminants can be anything. It can be solids, it can be solvents, right? It can be paint. It depends upon the industry, right? So in order to see that how it is going to be acting or how it is going to work, it can calculate. If you do the calculation, it is going to give you that annual solvent purchasing savings you are having around $8,000. Annual waste disposal savings is $1,920. Annual saving is closer to $10,000, and you're reducing your drum per year is by 90. Now, if you see over here, 2 drums per month, so it's around 24 drums, and here you're getting down to 19 drums. So you can see that how it is balancing on both the sides. On one side, it is saving on your virgin cost. On the other side, it is helping you to reduce the cost of the disposal also. So yes, it's a win-win situation where you are going to gain on both the ends. At the same time, you are protecting Mother Earth, yeah, not by not polluting it. Um, okay, so yeah, that was one. Then coming down to how role of simulation works. Okay, so again, I've talked much about simulations and how does the simulation work. I'm just going to give you the brief of how these models evaluate this stuff, or how do they evaluate the condition in which it is going to be working. Right. So if you see the advanced tools which are there, right? Aspen Plus specifically for academic use, Hysis, it's a more dynamic version of it. It takes up the data real time. So majority of the industries use Hysis. COMSOL multiphysics is also one of the good tool which is used for a couple of more mathematical based models, right? And all these things, first thing is to decide which particular, you can say, process separation you're going to use, right? Let's say I'll give you an example. We have two components in a mixture, and it is close boiling components. They are not having a significant difference in the boiling points. Now, out of all the process separation technologies that we know, the distillation is the first option for all the recovery units. Why? Because it is a one-step process. You feed in, you boil it, you distill it, and then you can just take out. It's a single step process. Whereas if you go for liquid extraction, adsorption, right, all these technologies, they need a stage two in order to get your pure product out. So that is the reason your capex, that is your capital expenditure, would be less compared to the ones with the other technologies if you're going with, right? So basically, that's first thing you have to decide, that which particular technology you're going to opt, whether it is towards the distillation side or it is towards the any other separation process, right? Then you have chemical and physical properties. This is very important. So to run the chemical physical properties of the chemicals, need to check if they are degrading at lower temperature or higher temperature, right? This will decide whether your distillation will be an atmospheric distillation or vacuum distillation. Because if some of the components or chemicals are degrading at higher temperatures, you cannot subject them to an atmospheric or maybe ambient temperature or pressure type of distillation, which we call a simple distillation, but it needs to undergo or it needs to have some kind of vacuum system. As you know, higher the vacuum, lower will be the boiling point, and this will prevent it from degradation. Other important thing, you have to see whether it is forming an azeotrope. Now, what is an azeotrope? Again, when the two chemicals are having very close boiling point, they will boil at the same time. There are low boiling azeotropes, high boiling azeotropes, depending upon which chemicals you're talking about. Water is very favorite for forming azeotropes. So that is a reason we have to check for that too, because that will change the process parameters. At the same time, it will also change the percentage purity you're going to get at the end of the process. Right now, simulations, why it is allowing the accurate distillation or maybe any sizing of it, whether it is heat exchanger. Let me give you an example. So there is an entire section of EDR which is used for the heat exchangers, different types of heat exchangers, whether it is plate and frame, or it is a shell and tube heat exchanger, or it is just a simple falling film type of a condenser type of a thing if you're using for the applications. It can easily be, you can say, designed, modified, calculated based on this particular parameters. Whatever you enter into the Aspen, it is going to give you based on that. So it designs it, it sizes, and it also gives you the efficiency at which it is going to, you can say, have the heat transfer coefficients and stuff. Simulations also have a couple of, you can say, drawbacks, which I'll take. There's just few of them I'll take later on. So whatever models that which we are using now, simulation uses thermodynamic models. Selection of thermodynamic model is also very important, because there are different models based on whether it is water based or whether it is, you can say, you have to use the models based on chemical nature of the structures. Let's say you have hydrocarbon mixture, then you have to use Pang Robinson. If it is water based, you are using NRTL. We have done all these UniFAC, UniQuac models, right? We used to do calculations of thermodynamics, but it was done, like you can say, using calculators and equations. But all these things are fed into the Aspen. So you just need to select the model, and it is going to do the calculation of properties required for your simulations automatically, right? So yes, maximizing efficiency is also one of the things which is very much important when you're talking about simulation. So too much of praising of Aspen. There are certain drawbacks of Aspen. Actually, it's not Aspen, but any simulations that you work. Again, it's done, you can say whatever you feed, it's going to give you the product out, right? It's not going to have its experience. So that's where there is, you can say, a lacking comes by. So whenever any design is done, we generally take a percentage of a conservative number, right? So if it is giving you a purity of 95%, you assume 92%, right? So I'm just telling you based on it is going to give you ideal condition, right? But again, there is no ideal condition in this world. There will be all real conditions where all the other different parameters are going to be affecting the process and it's going to direct your, you can say, process in whichever way it goes. Right. So, yes, let's dive now into the actual world of simulation. I'm going to take up a case study for you, which I've generated on my own. I mean, I cannot use the ones from my company, obviously. We have certain, you can say, privacy policies. So I have generated a case study for you. Now, why I have used ethanol water? Again, a good question. I think you might have. But the reason is water and ethanol, this is the most prominent combinations which we get for separation. At the same time, I know that the same thing is because ethanol is used for n number of applications, right? So this particular combination is very common and it is a low boiler. That means it is going to boil out first before the water. And third most important thing is that it forms an azeotrope at a certain composition, right? So that is what I wanted to show everything, how we can detect in a particular simulation. So that's the reason I've taken this particular case study. So case study works like this. I think I need to have a sip of water. Just give me 1 second. Okay, sorry for that. Let's go back. So we have, let's say, a company. It is generating around 48 kgs per day of solvent waste, right? Solvent water waste composition. It is having 50% ethanol, 49% of water, and let's say 1% of solids. Now, as it is, you can say waste, it might be containing solids, which can be debris, or it can be any other solids which is there, obviously in the dissolved form, or maybe in the suspended form. When it is in the suspended form, generally we use a kind of a pre-filtration to take it out, but if it's not, then it stays into it. So I've taken a solids which are there inside, and it is not going to harm our simulation anyways, but just to give you a real life example. Now, water, which is generally disposed of in the water bodies, we cannot do it at this particular composition of ethanol, right? So it needs to be first reduced, concentrated, or maybe then water ethanol is to be removed from it to the maximum it's possible, and then it can be disposed of. So this question is designing an Aspen simulation to recover greater than around 90% of uh, pure product and with any appropriate separation model. Right now, how do you define the process requirements for this? Now, what are the process requirements? As I told you, we start with defining the boiling points. This is the most important thing if you are selecting distillation as a separation process. And first thing that comes into your mind is distillation. So in here, ethanol boils at 17.8, water boils at 100 degrees C. There is a, you can say, sufficient difference of boiling point, or that's the reason we can use distillation, right? So what I'm going to discuss today is distillation, and we will be I'll be walking you through to my simulation, which I've already done, and then I'll make some changes and show how it varies. Right. So how does the simulation changes based on the change in the parameters? So let me stop sharing and just give me 1 second as I have to pull up my another screen. Okay, so um, sorry. Okay, I hope you can see the simulation screen. So basically, this is an Aspen version 14 that we are going to use. Whenever we start any kind of a simulation, we first generate a new file, and then first thing we enter is the components. Now, components here we have taken as water. So here there is a file version, right? Now, in this, you have to enter the particular chemical that you're looking for, because not all chemicals are so common that it will come automatically or it will be promptly available over there. So this particular components you can search from here, right? So if I enter ethanol, it's going to give me an equals. So because I just want ethanol, I don't want anything else to show me. So it is going to give me the entire, you can say, basic details about it. So it has the molecular formula, molecular weight, boiling point, and it is also going to tell you what is it's physically, basically it is having, right? As I've already added into it, I'm not going to take it up. So that's how I've added water, ethanol, and I've used for solids a C30 compound because it remains at the bottom, and it's inert, does not participate in the reaction. So this is going to mimic our solids, right? Then coming down to the components. So basically, when we learn about the components, we have to define the parameters and the methods. The method which is going to follow is NRTL because we have water. It's a thermodynamic model which is going to define or calculate different properties based on the model, right? And if you see, it is clearly showing you all the parameters. It's a common one. We have assumed the steam temperature and ambient temperature thing, and we are going to follow this. So this is the first setup which we are doing for properties. When we go down to simulation model, now when you see the simulation model, it looks something like this, right? This is my first step. First, I'll show you the main flow sheet. So if you see, this is called the palette at the bottom. The palette has different mass transfer operation and separation processes, columns, reactors, exchangers, and so forth, right? And from this, we have selected the ones which is called the columns. In the columns also, there are different types of it. I've taken the red frac, which is a fractional distillation column. So red frac is your distillate is going to be taken up from the top. Bottom is the waste product, which is coming from the bottom. In our case, the distillate is going to be ethanol and the bottom product is going to be water, right? Because water is a high boiler as compared to ethanol. Going down further, so this is how the simulation is going to be working. And first thing we have to decide is the configuration of it. Basically, how many stages you require, right? What type of reboiler it is going to be there, whether you want a total condenser or a partial condenser, how does the kettle or what types of basic, whether it is a thermosiphon or a kettle, because we need the reboiling, the heating at the bottom, which is going to vaporize the solvents. The solvents are going to be collected in the condenser, after condenser in the distillate tank. So it works like that, right? So that is what has been explained over here. We have defined the distillate rate based on the percentage, right? So if you can see the streams, So before we, defining this entire thing, we have to define the streams of it. Okay, so obviously bottom and distillate are the products. It won't be coming up. We have to define the feed. Now in the feed, we started it at room temperature, let's say 20 degrees C. Pressure is, let's say, 760. The mass is 200 kgs per hour. And we have given the mass fraction based on which, based on what we had our case study on, right? So it is giving us the fraction of each of them. If you see the composition of that, so you have reflux ratio, we have the distillate rate we have taken as 100. Why? Because my feed was 50%, close to 50% of ethanol. I want a complete ethanol out. So that is the reason we have used 100 kgs per hour as my distillate rate. And then you come down to reflux ratio, which is 2.2. It's just a one number. I can show you that if we change it, how it is going to act and how it is going to perform, right? So this is called our model, right? That we have defined. And then you have streams. We have to define at what height you want the feed. Generally, we have feed in the center. So we get the feed in the center. And the pressure we have maintained as 150 torr, that's under vacuum. The reason is we do not want the application to take place at a very high temperature. So that is the reason we have kept it under vacuum. We can remove this, not required, because the difference is not that much and the components are not boiling at higher temperatures. There is none of the component which can degrade. So this can very easily be done without vacuum. I'll show both of you, but both the condition. But right now, just with respect to vacuum, I'm going to continue. Condenser, you can define what could be the subcooled temperature. That means at the end of the condenser, what is the temperature you want as your product? So let's say if I'm writing down the subcooled temperature I want is 25 degrees C. Oh, my bad, sorry. I was over here. So it's a cool temperature is, let's say, 25 degrees C. I want to maintain that temperature. If I want to, I want my product to be at that temperature. So I have given this because this will calculate the extra cooling load, right? So if I don't add this, it is just going to utilize the latent heat of condensation because it's just going to convert it from vapor to liquid. But the temperature will not go down. That means it will not be cooled. Okay, so we have to give subcooling temperature so that it takes that into consideration, right? And there is a reboiler. We don't have to feed anything for the reboiler. So these are the basic parameters that we have to give. I've started with 14. I'll show you the configuration of the column. How does it work, right? So let's say column internals. Now, obviously, your distillation column that is there, right? Let's say this is 14 stages. We have introduced the feed on, let's say, above eighth feed or eighth stage. And then you have packing inside. I have designed a pack column, not the tray one, because this is a small diameter column. Unless you have 1 meter of diameter below that, it's very obvious that we will be using packed columns because there are so many advantages of it, right? And it is easy to handle. You can modify the parameters. So that is the reason we have used a pack column over here. So when you go down to the column internals, right, it will show you this is the basically column. This is how it will look like. Top half, bottom half. In between, there is a feed. You have, you can say from second to seventh, because first is your condenser, last is your reboiler. In between, whatever is there, those are your packed stages. Now, packed stages, we have divided into two. So it will be from 2 to 7 and then from 8 to 13. That will be divided it into two sections, right? I have used a packing which is from Sulzer. It's one of the company which sells, and it can be packed, it can be tray. I can show you the different types it is there. You have rushing rings, random packing, structured packing. Depending upon what you are looking for, we will be deciding it. I have used structured packing because I want minimum pressure drop across the column. So we have used Maratek structured packing, which is from Sulzer, and they have their different size ranges, which opt best for the application. Now this comes through experience and using the couple of types for longer period of time. The diameter I've given is 12 inch because that is somewhere the flow rate is going to define it. And then as each stage is around 10 inches, I have given it a 60 and 60. Now this can be changed. You can start with whatever figure basically you can start with that and you can start optimizing it. So this is an optimizing tool. You start with the basic stuff and then you add on the things as and when you require, right? So that's how it is working. And that's how I've given the basic, you can say, description of this, right? So these are the sections that we have been dividing it into. So what we did, we defined the components first. We defined the thermodynamic model, which is going to do the calculations for us. Then we came down to simulation. We made a block, basically entered the feed, took out the distillate and the bottom product. Then we define what are the parameters, how many stages we want, what is going to be the reflux ratio. Now, reflux ratio is very important because it will decide how you can say you are feeding in your product. Let's say, what is reflux? Basically, a fraction of your product you are feeding back into the rectification section, that is the top section of the distillation column. Now, when you feed it back into the system, this will improve the purity of your product. So basically, reflux ratio is decided. There are different types of reflux ratio, but we define optimum reflux ratio for different applications, right? And here this is too many trials and errors I've done. And then at the end, we've got 2.2 as my optimum one. You can start with the lower reflux ratio, because higher the reflux ratio, higher will be your condenser load, because that much more liquid you need to condense, reflux it, feed it back into the system, and the process needs to be in a closed loop. So that is the reason reflux ratio, we always start from very less, 1.1, 1.2, and then we go and increase depending upon your purity and which range you want your number of stages. Let's say you do not want a very tall column, right? In that case, you have to increase the reflux in order to get that purity, right? So yeah, so this is my model. Now we will be running it. So basically when I define or when I do entire thing, we have to go stepwise and define each parameter. Now each parameter has been defined. So I will run it. Now, when we run this simulation, right, and we have got the steam results at the bottom. Stream results means at the end of my simulation, what I'm getting as my product out at the top, what I'm getting it at the bottom. So if you see over here, these are my process parameters. Let's say I'll keep it in bar because we have taken it vacuum. Let's say torr. We had 760 as my in feed. 150 was my condenser pressure because I wanted vacuum, right? And then 25 was my subcooling temperature of my product, right? So if you can see, my bottom temperature is 54. It's not hitting high. It's low temperature, right? So as the boiling points are not that high, we won't be going with vacuum, but I wanted to show you vacuum application. That's the reason I've introduced it. If you go down, we generally go for mass fractions and mass flows. We started with 200 kgs per hour, where 100 was ethanol and remaining 98 was water, 2 was the solids at the bottom. Now, if you see my process, at the distillate, I'm getting 100% out, right? Where ethanol is 92, water is 7. And what is the percentage purity of ethanol? 92.5. Now, why it is so? We'll take it up. So this is the reason why ethanol is being pure, 92.5. It can pull to 93, 94, not higher than that. Why? Because at a specific concentration, it is going to form azeotrope, right? So 95.5 is a percentage. As soon as you go closer to that, it starts forming azeotrope and it will not separate. So that is the reason we cannot commit to the client that we will give you 99% pure in the distillation column, because the system doesn't work that way. It depends upon the properties, right? So maximum you can go to is 92, 93, 94 if you're taking a very tall column, but 92.5 is eventually the final version at a reasonable column height. So this is the purity that you're getting, right? The bottom solids remains in the bottom. You have the water going at the top. You have ethanol at the water is at the, some fraction of water is going because of the azeotrope formation. Otherwise, it's an overall uh, good good percentage of purity at the end of the process. Now this gives you an understanding of how does it work. We also need to know when we design a distillation column how much I need to spend for my condenser, reboiler, what is the kilowatts I'll be required for, because all these comes under utility. When you design a distillation column, you have to define the utility. What will be the chilled water capacity if a condenser is designed? If it's a reboiler, how much kilowatts will be required, right? So for that, you go down to the profiles. Now, when you go to profile, it will give you the temperature distribution at each level of your stage. All the stages, it will give you temperature distribution, also pressure. Now here we have not considered any pressure drop, but there will be definitely pressure drop. So we generally consider 5 to 10 torr of pressure drop across the packing. So if you see the heat duty, my condenser load is negative. So negative means it is going to take out that much amount of heat, 90 kilowatts, whereas my bottom is 99, that is my reboiler. Because reboiler is going to have a larger load. It's going to reboil, feed it back into the system, and the process continues. These are all the, you can say, mole fractions. I can go mass wise also, and it will give me everything in mass. We can say kgs per hour. And I can see that at the eighth feed or the eighth tray, I'm introducing 200 kgs per hour, right? That's how basically it works, that you have to decide where it is going to enter. Again, it's going to be distributed across the column, right? At the bottom, it also shows you how much you're going to drain it out and how much you're going to feed back into the system. So my total is 204. So liquid, this is the vapor content. So vapor goes back into the system, and the part of the bottom, which we call as bottom product, is taken out as the waste basically from the bottom, right? The results. And again, in this, let us see, we have the compositions on the mass basis, right? Because this is nothing but mass fractions, right? It also shows you the hydraulics. Now, this hydraulics plays a very important role in deciding what type of packing will be required, or if my packing is giving me very high pressure drop, right? What will be the density, viscosity across the column? Am I going closer to flooding of the column, or is it possible that my columns are going to get clogged, something like that? It is going to undergo fouling, whether it is showing me channeling, bypassing, which are the problems related to the pack column. Similar ways you have for tray columns also. So all these parameters, even foaming index. Now you know that some of the liquids are foaming in nature. Let's say ethanol water has little bit of foaming. Your MIBK, right? That is very, very prone to foaming. So basically, they need to check whether it is going to have a tendency of foaming or not. So that is foaming index over here. The flow parameters are defined, then reduced vapor factors. So all these things we don't use, but we generally look for the densities in order to see that it is having an easier, you can say, in and out of the process. Then you have on the results side, this is my overall results. Now, before I go to that, I would like to show you how does my hydraulics work, right? So we did some basic understanding of how does packing we are taking into consideration, right? What specific packing we are taking, and then we have to see the hydraulic plot. Now, if you see the hydraulic plot, it is completely blue. And if you see vapor and liquid distribution, they are very good. These is called the vapor liquid flow graphs. Okay, VLE basically, and it specifies the operating points and how does it work, right? And the stages at which it is going to be acting. So if I change this parameter, let's say I'm changing this to 10-inch. Okay, and I'm running it again. So we can see that it's still okay. That means it is able to handle. Why it is able to handle? Because it is approaching the flooding. If you cross 80%, it is, or 80, 18, 85%, it is approaching flooding, or it is going to flood the column, right? So that is the reason it is still working. Now, if I go a little bit lower, let's say 8 inches of the diameter, because my flow is not changing, right? I'm not changing my height. My hydraulic plot will show red. What does that mean? That means that your operating point is not up to mark. That means what your flow is not up to mark. It's either channeling or it is having issues related to the column design. Each and every stage is having an issue. Same ways, if I go on the higher side, obviously it's not cost effective, right? Let's say I'm taking 14 inches. 14-inch of a column, let's say I'm starting with that diameter. It is going to give me blue, but then it will show you red, yellow at the bottom. That means there is a pressure drop or very low flow rate over there, right? Why? Because the column design should be such that it could handle the flow rates. If it is too low or too high, it's not going to work. So you have to have optimum design for the vapor liquid transactions over the stages, right? Then you have column flooding again. So that is the reason we do not do flooding in this case. Let me go back to 12. What was my actual design? And that's how we are getting a perfect hydraulics. Along with that, we are not approaching the flooding. We are almost 50% to that. So I can go to 10 inch for sure, which is more probable right now as per the results and the design, what shows us. Right? So if you see, this is overall understanding of how does hydraulics work and how do you see that whether your column is working perfectly well, whether it is flooding or not, or whether your diameters or your measurements or your sizing is correct, right? And at the end, you have the results. Now, results give you a summary of all the, you can say, values that you're looking for. So the thing that I was talking about was this. So you have 90 kilowatts of heat duty and you have subcooling of 4. So you are adding to the condenser load. Similar ways, you have heat duty at the bottom and the boil up ratio. You need to check for the split fraction. So split fraction shows you that how distill and bottom has distribution of your ethanol. So ethanol is distributed like this and water, obviously, because we are not considering solids. We assume solids stays back at the bottom. So that will not be seen over here, right? So that is how our system is going to be working. Now, coming down to the thing that why it is not giving you more or higher purity, then for that, we will go to the properties. In properties, you know there is stored residue curves. Whenever you have 3 components, you can do residue curves and you can detect azeotropic compositions. So when you click onto the residue curve, it's going to ask you if you want to find azeotropes. So if you say yes, it's going to give you a panel where you need to decide or select which components you want to check for the azeotrope. So let's say I'm taking water and ethanol and then run. Now this is going to give me the report and this is going to be identifying whether it is forming azeotrope or not. So if you see over here, it is forming azeotrope at around 5% mass basis and 95% of ethanol. As soon as it hits this, comes closer to this, it is going to, sorry for that, it's my background music. So this is the point where it is going to form azeotrope. So this is called the unstable node, and it will define that whether it is going to form azeotrope or it is not going to form azeotrope. It's a low boiling or high boiling. So, and this is the reason why I selected ethanol and water, because I wanted to show that if azeotropic compositions are there, how it is going to behave. Now, coming down to the point, let's say we are having another high boiling component. This is a low boiling component I showed you. Let's say you're having a high boiling component. Now, I'll give you one more application that we are working right now, and it is very interesting. It's the lithium-ion batteries, which are used in the EVs right now, right? They use a chemical called NMP, which is N-methylpyrrolidone, right? Now, this NMP is very expensive. It is around $51 per gallon, and it's expensive for use, and they use in tons, right? So recovery of NMP is very much important, right? So again, NMP water, they have a huge difference in the boiling point. Sorry for that. I have a workshop on the back and they're making noise. Okay, so getting down to a component which is high boiling component, let's say NMP. So let me introduce an NMP. So I'm going to do entire thing now for water and NMP just to show you an understanding of how the higher component works. NMP is a common thing or because we have been using it couple of times, so it came automatically. If you can see, the boiling point is 204, boiling point of water is 100, and we will be running it under vacuum, so definitely it is going to work. So I'm going to take this as my component. Yes, I've added this in my system, right? My method is going to remain the same and I'm going to run it. I'm going to run the entire thing. It's going to show me that the process has been done. The calculation of the properties are done. Now I'll be going down to my simulation mode and I'm going to change my feed. Now feed initially was water and ethanol. Now I'm going to NMP. Let's say my NMP is 90% and my water is 10%. Remove my ethanol and solids. And let's run this. I'm not going to change the flow rate, right? Let's see what are the results. So if you see at the end of the process, it is going to give me the result. Now, why these results are off? Because I did not change my distillate rate. I was having 90% purity, right? So if you say 90% of purity, it would be closer to around 150, let's say. I'll start with that just to give you an understanding, right? And it is going to give me my product at the end of it. So it's around 129 kgs out of this. Still, it's not good enough. So I can go higher on 170, let's say. I'm not going too close to the exact concentrations just to show you an understanding of it. And it is still 88% that because there is some distillate of water coming in, right? I can change the vacuum. I can change the number of stages, right? Anything, all these parameters, again, you can optimize in order to give you the perfect results for this, right? So distillation column can be designed, it can be modified. There are a couple of things that you can take into considerations, right? There are certain things which you have to ignore when you're doing because we have to consider ideal conditions, right? So it will give you an overall understanding and a highlight of the process, and then you have to optimize it. Obviously, you have to do some calculations and compare. It's 99.9 times it is correct because again it's a simulation, it's not a human experience thing, so that's the reason it is going to vary, right? So that is basically what simulation works and it looks like. I have not gone much in the detail, but if you are having lower flow rates, now this was 200 kgs per hour, it was around 4800 kgs produced per day. But if you have lower versions of it, let's say you just have to treat 400 gallons or let's say 300 gallons, then we can also design batch modes. Now, how do that work? So if you go down to the batch models, right? So I can do a batch model over here, right? And this batch model is a small model where you can just feed in. It is a kind of a pot, his distillation pot. It will boil down. Distillate will be collected at the top, and from the bottom you can get the product. Now in this also you can introduce if you want number of stages, your reflux. It can be full reflux, complete reflux, or it can be partial reflux, right? And all these things work very well when you can say design it based on your parameters and applications, right? So you can design this. We can again same ways we can add the properties, feed, distillate, bottom. So when I enter them, it will show me what I need to specify. And then when I click onto that, let's say this is my feed, right? So this is a second block, B2. So it will generate a B2 over here, right? And then B2 will have all the setups, same ways as I did for my distillation column, right? Here the stages are, let's say, I don't want any column on the top. I just want a simple batch to boil out. There is a jacket, which will be having heated oil, which will be heating the surface. It will distillate out and it will be collected, right? So we do not need to enter this, right? Then you have the streams. Which streams are you're going to start with? Let's say S1 is my stream. I want mass basis, volume basis. You can select accordingly. You need to give dimensions of the pot which you want to design, right? It can do it automatically, but then the parameters will change, which you need to add and do the surface. I'm not going to go much in detail of this because I need at least 15-20 minutes with you guys for questions. That is the reason I'm not going to go much in the details. But yes, I just wanted to give you an understanding of this also you can do. You can also do exchangers, right? There are so many different types of exchangers, right? Let's say if I'm taking this and I can plug this on, right? And if you click onto this, sorry, my bad. Right? So the heat exchanger again, cold side, hot side, you can decide on what will be on the cooling side, what will be the temperature, what is the range you want, what will be the delta T that you are expecting at the end of the process, how much you want to subcool, and everything you can define. You have reactors, there are CSTRs, there are PFR models, right? You can introduce your components and obviously the parameters. There are stoichiometric reactors where you have to enter the reactions. Let's say you're doing a catalytic reaction. Then you can introduce the catalytic reaction. You can specify the catalyst because it has the database, which will be taking up the details from that, and then it is going to solve it for you. Right, then you have electrolyzers also. So many things can be opted on. You can try doing it, right? You have solids, you have mixers, splitters, right? Because you don't have one model, you have couple of unit operations. You can make an entire flow sheet onto this. There is a heat exchanger, distillation column if you want to have a preheater, or you want to recover the heat at the end of the process. Anything is possible, you can use this. And the beauty of this is what you can modify as many times you want and without disturbing the actual process, right? Once you modify and optimize on this, then you can make the corrections, or you can design a small pilot plant. Let's say you are an entrepreneur, you want to introduce a new system. This is the best way to do it, right? First, you can say confirmations of the parameters from this, and then you can make maybe a pilot plant or a plant on a larger scale. Right? So yeah, so that's, I think so. Let me share my screen again with my slides. This was all from the side of simulation. And last one, I think so. Is my slides visible? Sorry.
Yes, ma'am, it is visible.
Yes.
Is it?
We are on the
Okay.
case study.
Okay, perfect. Because I thought maybe it's working or not. Okay, so yeah, that was all from my side. I think so I've stopped sharing my screen because I want to take questions from you. I know you might be having questions on your end. So let's take up the questions. And other than that, if you have any questions related to simulation, I'm keeping the simulations open right now. I'm not closing it up. So yes, sir, we are now open for the question answers.
Yes, participants, you can raise your hand now so that I can unmute those participants for asking the question.
Yeah, can I ask a question, sir?
Yes, yes, please.
Yeah, thank you very much, ma'am. I mean, it was very informative and nice. I have had an experience with Ude, that is Tyson Group now, in the same process engineer. So it was really very nice to hear this from you.
Thank
But
you.
now I'm for a small this thing acquire in Vadodara. This software. I mean, suppose if I go for one Hysis software, when
Yeah.
I design a distillation column, does it also give me the heat exchanger design for the reboiler and all?
No, it will not give you the design of the distillation. It will give you the design of the distillation column, not the reboiler and the condenser. It will just give you the load. So it will tell you that your load is, let's say, 15 or 50 kilowatts. And then you have to go in the EDR, which is a different section of Aspen, and you can design it. You know your kilowatts, you can enter your kilowatts, and it is going to give you the flow rate based on that. So it makes your life simpler, but it is not going to design it.
Okay, okay. No, I mean, particularly the aspects like, fouling factor when there are solids in the bottom
Yes,
section, they are really
yes.
very critical to handle in design. So that's why I was
And
asking you whether.
yeah, so you can introduce the fouling factor in your calculations. Even the EDR, which is the exchanger version of Aspen, it takes all these things into consideration. It considers fouling factors both on the shell side as well as tube sides, right? If you're going for a shell and tube heat exchanger, right? And it also defines whether it is going to have any issues related to it going forward. So
Yeah, my next question is, I mean, normally what percentage you keep for the flooding? 70%? Or
it depends upon what is the feed which we are getting, but we do not modify this feed, whatever it comes in based on the analysis, unless and until it is free of solids, we can definitely treat that. And also we need to know what is its chemical composition, because if it is not, you can say optimum difference in the boiling point is not there, we cannot use distillation. We have to opt for a different set of operations, right?
and the type of distillation I have to decide first. I mean, the whether it is extractive, it's azeotropic, it's steam distillation, or all those things I have to decide first.
You have to decide. Decide, because the reason is, as I showed you right now, that ethanol and water forms azeotrope. So when, let's say, you are not knowing it, right, that why it is it's an azeotrope, let's say, and you are getting 92.5, you try to increase the number of stages, you're trying to increase the reflux ratio in order to optimize and see why it is not going high. So that is first thing should come into your mind, that there is possibility that this combination of solvents might be forming an azeotrope. Let me check it. And that Aspen has that version, right? So you can just check always, you can go onto that and you can check the azeotropic compositions. It also gives you the pressure, temperature curves. It gives you the change in the composition with respect to time on the stage wise, right? So there are, you can say, on the side where you can have the understanding through the trends, how is it varying, right? It can move to dynamic mode also. So dynamic means it changes with respect to time. Let's say if you're adding the data with respect to time, it will give you the trend also. So yeah, all these things are also possible into that. But yes, you have to decide initial parameters for sure. And again, it's an estimation, right?
Yeah,
Basically.
yeah. Yes, yes. You're right. Thank you. Thank you, ma'am. Thanks a lot.
Thank you so much. Yeah. I had hands up initially. Maybe at the starting of the session, they were having questions. Now they don't have any questions. Maybe there
Might
are
be
two
they are
things.
satisfied.
Either they have understood it thoroughly well or they have not got it at all.
May I ask you a question?
Yeah, please go ahead. So,
Ma'am, very nicely, very nice and fluent presentation. I have one
thank you.
question. If we have a 5% ethanol and or 1 or 2% NMP in
Mm.
water, so
Mm.
did you tried uh, simulation for
We
this
can try
particular
that,
kind of a
but yeah, but when you do that, what will happen, you will be having all three coming out. Basically, initially there will be water and NMP coming out together. Sorry, water and ethanol coming out together. And then NMP you have to boil a lot because NMP's boiling point is 204. So it's going to stay at the bottom, right? You can separate them out, but what will come out will be your water and your ethanol together. So there will be you can say a mixture of ethanol water as a distillate, and NMP will be there at the bottom because NMP doesn't form azeotrope with either ethanol or water. So it can easily be removed from the bottom as a waste, basically,
Mhm. Okay.
right?
No, actually, I just wanted to ask you that if we have a 5% ethanol and 95% water,
Hmm.
okay, so did you tried simulation for this particular kind of composition?
Yes, there is no separation. You cannot see separation because it is going to remain. The composition which is coming out and composition which is staying back at the bottom is going
That
to remain the
because
same.
this azeotrophs is
Because
forming.
exactly, and that is the reason if you want to treat this, there are methods. You have sieve technology, right? So
Mhm.
the generally what ethanol producers do, they do distillation initially. Once they come down to concentrated ethanol, and then they move down to sieve technology, and then they improve that to 99%.
Mhm.
So there are methods, but again, they are cost effective, and then you have to check for the. So generally, they recommend having 99% ethanol in pharmaceuticals. So they
Mhm.
need to have a secondary process for that.
Right. That molecular sieve or something
Molecular
using
sieves,
solvent.
solvents,
Right.
exactly.
Okay. But actually, in wastewater treatment, the wastewater that consists of maybe in a trace amount of the solvent. Uh,
Yes.
some of the solvents they are valuable, costlier one.
Yeah.
Okay, so in that case, uh, how can it possible to use this simulation? Like trace amount of solvent is with the wastewater, like 2 or 3%. Assume like 2 or 3% NMP is with the water,
Hmm.
or maybe
Yeah.
5% ethanol with the water, with the
Yeah.
wastewater.
Right. Don't you think so? The capital cost is going to be too expensive for this instead of the disposal cost. So again, you have to use, you can say, what you can calculated things. These are all you can say. You have to make a judgment based on how exactly it is feasible or not, right? Because
Hmm.
5%, 3%, you cannot use distillation columns because they are in like hundreds of thousands for construction. So
Right.
basically, for them, disposal will be better. I'll just call the hall and they'll haul it out. We don't need to do that, right?
No, no.
So even here also, the companies
Yes,
do
yes.
not do
Cost
that.
economics we have to consider.
Yeah, but yes, distillation will not work.
Yeah.
That was the answer.
And if,
Uh,
yeah, okay, it's okay.
no problem.
No, please,
Uh,
carry.
okay. Michal Bhavsar. We have one question from Michal Bhavsar. Please unmute yourself.
And it would be better
Yes,
if you
yes.
start your camera also
Dear ma'am, I
because
want to.
Yes. Please on your camera.
Yeah,
Turn on your camera, please.
wait. Uh,
no problem, Michelle. You can continue. That's fine.
Yeah, it's dinner time right now. That's why. Maybe.
It's fine. Michelle, you can continue with the question.
yes, yes. I was having a question like that. If this is not a thermal process, if it is ETP or if it is RO or if it is, then it will work the stimulation on this uh, software.
Can you repeat your question, Michelle? You were breaking in between. I'm not sure what you were saying. Can
I
you
was
please
just
repeat
asking
your
that
question?
if thermal process.
Michelle, your voice is
Hello,
unaudible. Can you please check with your
hello.
network? Yes, yes. Now it's audible.
Yeah, now it's
Yes,
audible.
yeah. I was just asking that if the process is not non-thermal, like it is for a ETP or it is for the RO or it is like for the NF, then this such kind of simulation process will occur in the software.
No, I don't think so. We have RO, reverse osmosis, and ultrafiltration. All these things you need to calculate the semi-permeable membrane type, right? And you have to have the design based on that. As far as I know, you have to generate a user model. There is an option given to you for a generating user model. So you have to introduce too many
Okay.
parameters based on that if you want to do it. But the ready palette that you have, that doesn't have any of the option based on that, right?
Okay. Thank
Okay.
you.
No problem.
Kimshuk Desai. Kimshuk Desai, please unmute yourself and turn on your
Hello.
video, please.
Am I audible?
Yes, yes, you are audible. Kindly turn on
Yeah.
your video, please.
I'm not able to turn it on.
It's okay. Go ahead.
Okay.
Hello, madam. Good evening and
Good
good
evening.
morning for you. I was one of your student during SCAT in
I
2010
remember
physics.
you, Kimshuk. I remember you. How are you?
Yeah, yes, nice to see you after such a long time.
Yeah, thank you. Same here. I mean, I cannot
Uh,
say that because I cannot see you.
yes, yes.
Yes,
Just
Kimshuk,
a
go
one
ahead.
question, madam.
Mhm,
Uh, let's say, for example, there's a leaching process is there, and
mhm,
in packing material, as a packing material, if we want to use some of the solid component from which we want to leach a valuable component,
hmm,
can we use that as a packing material and we can just pass the vaporized solvent through that packing
hmm,
material, and whatever the component is coming outside,
hmm.
we can check whether we are recovering in raffinate or in condensate. Is it this kind of simulation is possible for the similar?
Yes, you can make leaching option possible because it is something similar to a pack column, right? So leaching is what you have a solid is there, and then you are passing a solvent or maybe a vaporized solvent through it. You are condensing or maybe you're taking out the leach solvent at the bottom, right? So it is possible, but again, you have to formulate that. The ready palette doesn't have a leaching application so forth, but you can definitely make packings. You must be knowing that packing again. That packing needs to be
Hmm.
there in the list of the packing that they have, okay, already available. Or you have to give the porosity. There is a possibility of adding something from outside. I mean, you can add from your side, but you need too many parameters for that. So if you
Hmm.
enter all those things, there is possibility. And then again, you have to have a combination of it. So let's say if you want a vaporized feed, you have to provide a preheater. So it will be vaporized, partially vaporized, and that mixture can get into the system, right?
Right, right.
So yeah, it's possible, but again, it's too much of work in case if you have to make a complete new process or a model,
Mhm. Right, right.
right?
Thank you for your
Yeah.
inputs.
Thanks a lot.
Yes, Mr. Amir Mullah.
Madam, am I
You may ask.
audible?
Yes, you
Yeah,
are
you are.
audible.
You are
I am
audible.
not from a chemical engineering background. I am from environmental science,
Okay,
and
sir.
we have UG and PG courses at our department. Okay, I'm
Okay.
from Ferguson College, Pune. My
Okay.
question is simple. Like I was listening it with a curiosity, and I understood few things. Okay, most of the things are related with the distillation process
Mm-hmm.
and with the simulations before running in a distillation column or before doing it practically. You are looking at the probability of the process. That much I
Right.
understood, but
Perfect.
if you comment it within a simple thing, like how it can be useful for ordinary processes where distillation is not there, but we have conventional wastewater processes, or even nowadays in India also we have few water treatment plants or
Mm-hmm.
ETP and STPs, where we have RO kind of treatment options are available. Okay, filtration
Right.
systems are available.
Filtration
So
systems. Right.
how this simulation process is effective for conventional and RO based water treatments, if it is,
Yes.
or it is only applicable to the distillations?
No, it is not only applicable to the distillation. You are correct. Let's say if you're talking about a wastewater treatment, right? You want to design a clarifier. I'm just giving you an example. So that clarifier can be designed, or you can say you can define what will be the speed of the clarifier, what will be the size of the clarifier, what will be the, you can say, liquid which will be getting at the top, what will be the purity of that, or similar type. You can do that. Now, Aspen does not have one package. It is having n number of packages, which includes adsorption. There are certain, you can say, analytical options also available over there. So basically, what you're talking about, RO ultrafiltration, I think so. One of the other participant also asked the same thing. You can definitely get into that, but again, the thing is what you have to use that specific set or program for doing it, because right now what we are having a specific package because we use that, right? But many of there are n number. If you go to the website of Aspen, they are having n number of packages which you can opt for, right? And in that they might be having couple of you can say applications based on you can say defining or designing a wastewater treatment. You have dryer designs, right? You can design the tray dryers, plate dryers. You have those designs also available. You have adsorption columns, then you have absorption columns, then you have, as I said, leaching can be possibly done. So from any, you can see unit operation that you're thinking in your mind that can be done, but depending upon that, you need that set of, you can say, program available in that. So there are packages, we call it as a modules. You can opt for that, and then definitely it can work. And it's a good tool to have a hands-on, whether it is environmental researchers or scientists or maybe students or academicians. It's good for all. I mean, it's a starting thing, and once you get into that, it's easier for you to do. And again, it's hands-on. You can do as and when whatever you want. Only thing is you need to add the parameters based on your process. I hope I made my things clear. Okay.
Yes,
Thank
ma'am.
you.
Thank
Ma'am,
Thank
ma'am,
you.
multiple effect evaporation system is one of the component in wastewater treatment. It is
Yes, we
being
can do
used
that.
as a tertiary treatment, right?
Yes.
So it's a heat exchanger. So
Yes.
that simulation is possible in that
It is possible.
multiple effect
It is
evaporation
possible.
system.
You can do multi-effect evaporators. You can do
Mm.
falling film evaporators design, right? All these can be done into it because there are so many options available for that. Yeah, I can take two more
Yes,
questions.
there are two more questions. One is from Pushpajit Barad and another is from Dharmesh Patel. Pushpajit
Sure.
sir, you can please unmute and turn your camera on. Hello, Dharmesh Patel, you can also turn your camera on by the time and unmute yourself.
Don't ask for camera. Just ask the
Yes, yes,
question.
yeah. If you can't
Okay,
operate camera, please ask the question.
you are already unmute, Pushpajit Barad. You can ask the question, please.
Might be
Okay,
they
He
have
just,
Dharmesh
I
phone
think
there.
Patel.
so. I think so. He just want to say hi. Hi. Okay. Let's move on to the next one.
Okay, Dharmesh Patel. I guess he also wants to say hi two times. He waved for two times.
Okay. Hi.
Okay.
Hi. Let's, yeah, that's, I think so.
Can I
Those
ask
are
one
all the
more question,
questions.
ma'am?
Yes, yes,
Last
yes.
one.
Yeah, yeah, please
Yes,
go ahead.
yes. Mhm.
How much is the like cost for this technology? Do we need to take a license copies of it, or
Yes. So
it is a freely available, or like trial versions are there?
You can try for the trial versions, but as far as I know, we do not have you can say free versions available. You have to buy the license copy of that. And I remember because I was the one who bought it in my department. So you can buy it in Aspen from the there is a licensing. As if you go on Aspen India, they have their licensing entire procedure given to you, and you can buy it. It's not that expensive for a university or a college based. I don't think so. It's that expensive to have a good tool for. And even the students get benefited from this a lot. So maybe you can think of.
Yes. One last question, Nan, but
Sure.
Nan, please unmute yourself. Okay, I suppose, is there any more question? No. I suppose let's end our session here. Thank you so much, madam, for giving such an informative session. I'm damn sure that all the participants would be benefited from this. And if suppose they are having any queries, further queries, I shall give your email ID to them so that they can communicate with you.
Yeah, no problem. Thank you
Okay,
so much
ma'am.
for having me and
Okay,
giving me
ma'am.
this opportunity to give whatever knowledge, little bit of whatever I'm having. And it was a wonderful session. And do share the feedbacks.
Yeah,
For
sure.
sure, ma'am. For sure. The pleasure was all ours. Okay.
Okay.
Thank
Thank you so much.
Thank
Good,
you.
thank you,
Thank
ma'am.
you.
good night, everyone. Take care.
Good
Yeah,
night.
good
Bye bye.
night. And good
Good
day to
night.
you. Okay, participants, good night to each and everyone. You may please leave the meeting and we shall meet tomorrow at around 5:50 or 5:55 p.m. Tomorrow we are having two very important sessions with very highly experienced faculty members, one from Naidu sir and the another one from Parik sir, both having more than 40-50 years of experience in their relevant field. So do join tomorrow on time. Thank you so much. Good night.
Good night, all.